So first of all, we just go through what is induction, because that's like the main idea behind recursion. It's a proof technique where if you have to prove some claim, you first for like all natural numbers n, the first thing you'll do is you'll prove it for when n is equal to 1. And then you will assume that the claim holds when for like some value, and then go to n plus 1, prove it for n plus 1. So,
Hi Shreya, sorry for interrupting. Just a second. Can you hear me?
yes, I can hear.
Okay, amazing. We'll make you host and leave. And if there's anything needed in the between, feel free to give me a call. And at the end, once it's over, in case one of us isn't there, you can just end the meeting.
Yeah, okay.
Sounds good. Thank you so much.
Thank you. Bye. Okay. Yeah, so that is the general sort of idea that let's just do one silly example to understand the idea behind induction. So it's like prove that 1 plus 2 plus until n is n times n plus 1 by 2. So yeah, the way to do this would probably be key first you assume it for n equal to 1. Not don't assume it, you show it for n equal 1, which is just saying that 1 is equal to 1 times 1 plus 1 by 2, which is true. And then for a general case, just suppose that you've proven it for like some k. So you assume that 1 plus 2 plus k is equal to k times k plus 1 by 2. And now the claim for, we have to show that the claim holds for k plus 1, which is just k plus 1. So this is just fairly straightforward because this part we know that so the LHS is equal to k times k plus 1 by 2 plus k plus 1, and then it's just some algebra which will give you k that is equal to k times k plus 1 k plus 2 by 2. So the point is that in proving this directly for every integer is kind of weird because you have a summation and you can do it directly, but that's not particularly nice. So you will, so like the general sort of idea over here is that if I had to convince someone that induction works, what I would say is that how can it not work? Like when would it stop working? It works for 1, so it has to hold for 2 also, and that holds for 3, and so on. So like if it doesn't work, then when will it stop working? Where's the least k for which the claim actually does not hold? And then it holds, but it holds for k minus 1 because that's like the least k. So that's a contradiction, right? Because it holds for k minus 1, but it doesn't hold for k. But you prove that if it holds for k, then it has to work for k plus 1. So like this thing is actually called the well-ordering principle, this argument. Which states that every non-empty subset of naturals has a least element. So this is equivalent to the principle of mathematical induction. Sometimes it's just helpful to use like the well-ordering principle, which why not? But they're in general the same, so it's not big deal. But also this gives you the freedom that it's not just k minus 1 that is true. If like you assume k is the least, if you do something like assume for the sake of contradiction that the claim does not hold, right? And then like that is just saying this S of, when S is the set of numbers where the claim doesn't hold, then S is non-empty. So then you can use well-ordering principle and consider the least such element. So this actually gives you more freedom than considering just k minus 1, right? You have like all the numbers up to k minus 1 also, because k is the least. So that is in fact the idea behind something called strong induction, where over here, like instead of assuming for n equal k alone, you can also assume for everything up to k. And this is also equivalent. It's like not very hard to show the equivalence. It's quite a nice exercise, I would say. Okay. Yeah, so like induction is, so the point I'm trying to make is that if you have an inductive sort of proof, then there's also well-ordering principle, and least element may remind you of extreme elements. So if you have a problem which is done with an inductive approach, then you may not see like the word induction in the solution. You may see it as something extreme, or even like well-ordering principle or induction that is fairly normal. It's also some extremal thing. Or like an algorithm where you have an invariant, right? Because then if you have some invariant and then you go from n, you manage to go to n minus 1, like n is some strange value, like there is something whose value is n, and then you can go through the algorithm and go to n minus 1, right? So then it's like induction, you can induct on this particular n to show that it is that the algorithm will terminate or whatever it is you want to show. So like inductive ideas are in general not only seen in induction problems. Okay, so is this okay for most people?
Yeah.
Okay.
Yes.
Okay. So now for recursion, just talking about recursion is not very helpful. So let's just do this problem. Okay, so we have, it's like a normal sort of basketball game, and with 4 people, and you always, if A has the ball, then A can pass it to B, C, or D, whoever A wants. So like obviously A will pass to some other person. A will not keep the ball in any turn. So we have to find out how many ways, like it starts with A, and then some things will happen, like it will go through some passes, and then after 7 passes, it should come back to A. So yes, this is one possibility. It will go from A to B, and then B will pass to D, D will pass to A, to D, to C, to D, and back. And how many ways is this possible? So since like the point of this is recursion, I will just go through the solution. So the point is that if you have say 6 moves, the first 6 moves are done, then there's only one thing which can happen, right? When you say that it will come back to A. So the point is that if you have a sequence of 6 moves already given to you, then all that means is that you can always append an A to that. Like you do the first 6 moves as you wish, and after that, whoever has the ball will just pass it to A. So that works mostly, except if after 6 passes, A still has the ball, then you have a problem because A can't pass back to himself or herself. So basically, if the number of ways over here is an, then for an, any of the other 3 to the 6, it says 6 because at every turn you have like 3 choices of who to pass to, and 6 passes. So that's 3 to the 6. But then you have to subtract the number of times when the ball is with A, the ball is already with A, so that's like minus A6. If the answer, let's say we replace the 7 by 6, then the answer is A6, and then it's A7. So here it feels like you have made some non-trivial progress. Right? Earlier you had to solve it for 7, now you have to solve it for 6. Okay. Sorry. So yeah, it does seem like some non-trivial progress. Even though like it's not a big deal to go from having to solve from 7 to 6, but the point is that you can also go from 6 to 7, right? So by the same argument, you get key a raised to 6 is 3 raised to 5 minus a5, and so on. So here what you would do is you would write this more generally as an is equal to 3 raised to n minus 1 minus n minus 1, and then just derive everything. So a1, you know, is like 1 pass and nothing happens, right? So a cannot pass once and it comes back to a, that's not possible. So like a1 is just 0. And then by the same logic, we'll get a2 is equal to 3 raised to 1 minus a1 is equal to 3, and so on. So like a3 is equal to 3 squared, a2 is equal to 6, and so on. So now it's just some computation. You have to find a7, but that shouldn't be very, very difficult, right? It's doable. 81. Okay, anyway, this is just some computation which is unfortunately gets messier after this, but it's okay.
That's 183.
Okay. 183. A7.
And 546.
Okay. Yes. Finally. Even if the answer is not so correct. So the point is you can do this like generally if you have something which you have to find for some value of n, and you manage to get that in terms of thing like the value for n minus 1, then you can extend like this. Of course, in most reasonable problems, you will hope keep small. Like here, it's just 7, so that was doable. But it's all right. Like usually, if it's the intended solution, then this will be doable. So that's kind of the idea, to just here the moment when you turn the problem, like when you turn around and you suddenly know what to do, is when you give it a name, that you call it an, and then everything starts working out. Just giving it a variable makes things starts making sense. Just okay, is this clear?
Yes.
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 Okay, so also like in general, let's just see how an looks usually. So if you have to solve this, then the first okay, so the first thing to try would maybe be just to guess, which does not seem to be going well.
Maybe
But anyway,
ternary representation, like convert all numbers into ternary.
yes, that does seem like the way to go. Okay, so let's just see. This is 10 base 3. This is 20. This is
I think
9210. Okay. what is this? 27, 54,
20.
2010, right?
No, because 54 plus 6. 6 is 2 times.
Right, sorry. Okay. This thing is, what is it? 183 is 3 into
81 plus 21. 21, so I think it will be
20210.
20210.
Nice. Okay, and this thing
This
is
is 202020.
202020.
20.
Amazing. Yeah, I think this is alright. Is it? Should be okay.
wait, I think it'll also be on the parity of n. Like
Yeah,
the parity.
like here it is 20, here is 2020. So, and
Then-
here it's 2020. So it will probably repeat. So like,
This easy, right? Like it becomes something like 3 to the n, 3 to the n plus 2 minus 3 to the n plus 1. And then that's 2 to the power of 3 to the n plus 1, something like that. And then inductive, for the every alternate one, it's sort of like adding with 0.
yeah, that is true. But I'm thinking more like you want an actual algebraic lesson to find it in base 10 instead of finding it in base 3 and then converting.
But that's also quite doable, right? Like it'll become a GP for even
Yeah.
now people different.
Yes, that is nice. So what is it? It's like 8 1 plus 1 is equal to, you have the 2 0 and then you move it. 9 times 8 1 minus 1, because like here you have this 2 0 2 0 2 0 and then you move it by something, which is this is basically like adding 2 zeros and then you add 6. This is not so nice. Okay. So now let's actually do this. Instead of being, let's do this in like the more bullheaded way, because that is nice to know. It's nice to know how to do it in the bullheaded way. Okay, so you will of course write key A 2k plus 1 is equal to fk, let's say. Then you have fk plus 1 is equal to 9fk plus 6. And then you do, okay, so the point is key, if you have like a recursion, I'll just show you how to do this one. And then I will explain the general method. And then it's fk is equal to 6, which is equal to fk minus 9 times f. Now we bring it over to this side because we want to get rid of the constant terms in general. That is a nice thing to do with recursion. Okay, and this turns out factors. Okay, so we try to find the roots of the division, x square minus 10x plus 9. I'll explain why we do this. It's okay, so one way to look at it is you're looking for roots, non-zero roots of xk plus 1 minus 10x to the k plus 9x to the k minus 1 equals 0. And then you just cancel the x terms with this. So this is x minus 9 times x minus 1. So what this is saying is, because here like I said x to the k plus 1. So in general, if you have something like x, like a powers of 9, so like 9 to the k or 1 to the k, both of these are roots to the equation, to this equation, to like the recurrence itself. So you can check not the original recurrence, but this equation, this recurrence.
Yeah, I think I have another method of doing this.
Okay.
So we'll get the an is something like 3 to the n minus 1 minus 3 to the n minus 2 plus 3 to the n minus 3 minus 3 to the n minus 4, like that. And then we do
TP formula.
3 to the n minus of minus 1 to the power of n by 4, because 4 is 3 minus or minus 1. Something like that. That's how
I
it done.
see. Basically, you're trying to use GP formula, right? That is nice. That's smart. That should work out.
That will also explain the parity because when n is even, the minus 1 to the n will give something different.
Oh, right, of course. You would like factor out the 20 and then this. That 20 is not 20, by the way, it is 6. But anyways. Okay, I'll talk about that. I will mention like your method later. Okay, so if you look at only this recurrence, fk plus 1 minus 10fk plus 9fk minus 1 equals 0. Then 9 to the k and 1 to the k. Like fk equal 9 to the k always, and fk always equal to 1 to the k are both roots. That's like, okay, that is easy to see. Let's just say. So the key idea is that because we got rid of the constant terms, if we have one, just a second. So if we have one value of f, or if we have one function f satisfying this, and then we have another function f dash which satisfies fk plus 1 minus f dash k plus 1, it's 10 f dash k plus 9 f dash k minus 1 equals 0, then because this is like completely linear, you can also say that for the function f, not f, h is okay, h. Okay, sorry about that. So if we have a function defined by h is equal to f plus f dash, so like hk is equal to fk plus f dash k. So then f h because like sorry, I lost you somewhere and okay. Till where did you guys hear? At what point did I break? Someone just. Okay. Okay, so I was saying something about so the point is if we have like two solutions to this recurrence, then we can add them. And also if we have another function, not h, g. G is such a weird name. Okay, gk, which is some constant times f.
Screen is not visible.
Achha, okay, I have to start sharing it. No, I lost my host powers. Now I can't share. Wait, I'll call Shreya. Just sorry about that. I just lost my host powers. Now I have to call.
Where I think you have to give her host powers.
Wait, I turned into the host.
Yeah.
That's odd.
Yeah, you just okay. Go to I think me. I'm not sure how to make people host. Oh, okay. Thank you. I can share. Okay, can you see it?
Yeah.
Yes.
Okay. So, yes. So if you select, yes, did I tell you about this, how you can add them? Add two solutions to this.
Think you're almost at that for now.
Can
Hmm.
anyone tell what happened? I just have to.
Okay, okay, I'll just. So if you have this recurrence, so like let's not worry about the original recurrence, and we took this thing and remove the constant term by doing this. So we have this, which is like totally linear. And now we'll try to do something like, see, if you have two solutions to this equation, so we solved this as, we didn't solve it completely. We got 9 to the k and 1 to the k are both solutions. And now we are saying if we have two solutions, f and f dash, then f plus f dash is also a solution to this equation, this relation. And also, if you multiply it by a scalar, that's just because over here, like you can just add a c everywhere, and it will become g. Okay, so basically, what that's saying is, if we have two solutions, which are 9 raised to k and 1 raised to k, which is just 1, then everything of the form
Sorry, is the class recording?
fk. I think it is, yes.
Yes.
Oh,
Yes. So everything of the form fk is equal to c times c1 times 9 to the k plus c2 times 1 to the k. I'll just write it for no good reason. All of these are solutions. And that's just because 9 raised to k is a solution to this recurrence. And then you multiply it by a scalar constant to get c1 times 9 to the k is a solution. And then c2 times 1 is c2 is a solution in general. So c2 times 1 is no, sorry. So like you can add the two solutions to get c1 times 9 to the k plus c2 is a solution. So this is the general solution to this particular example. And the reason this covers all the solutions is mostly key. So you have like two value fixed, right? So you have f1 is given to you, f1 is given, f2 is given, and you want to choose c1 and c2 such that this is the solution, right? Because if it's the solution, because if this is the case for f1 and f2, then it is the case for all k. That's just some induction which will work. That you can prove by induction mostly. So the point is that you will have some system of linear equations over here. So you'll have something like c1 times 9 to the k plus not k times 9 raised to 1 plus c2 times 1 raised to 1 is equal to f1, which is given to you. And you also have c1 times 9 squared plus c2 times 1 squared is equal to f2. So now f1 and if you know f1 and f2, then you can find c1 and c2, and they are determined uniquely. Most like you can verify key these things have a unique solution. So yes, this will be the most general solution because these work and these are the case most. So anyways, yeah, this is the more general solution. So now we have to just solve it because we know the value of f1 and f2 and get what we'll be doing? Fk in general. So what is f1? F1 is equal to a3, which is 6. Okay. and F2 is equal to A5, which is that is A5, 1 now. So now we just have to solve this thing quick just to make sure everyone is getting it. Can someone help me solve this? Just to find the closed form. Okay, better, go ahead.
No, I think A5 is actually 60 then, right? It's
What was 60? F5?
A5.
No, A4 was 60. A5 is 183.
Oh, yes, I see. Then wouldn't that mean that A3 was 21?
Yes, A3 is 21. Okay, can you just solve this one? Because it's too much algebra. Oh, sorry. Okay, A5 is 60, sorry. And A3 is, I was reading this part. A5 is 60. And A3 is 6. Okay, nice. So C1 times 9 is 2. 6 and C1 times 9 is 2. C1 times 72. 54. Now we will get some messy answer.
3 by 4.
3 by 4. Okay, that's not that bad. Okay, and C2 is equal to 9 times 27 by 4. 6 minus 27 by 4 is minus.
It would be minus 3 by 4.
Yes,
Yes.
minus 3 by 4. Yes, so we have got Fk in general is equal to 3 by 4 times 9 raised to k plus minus 3 by 4, which is not extremely nice, but it's okay. At least we have a closed form. So usually, like, you won't use a closed form for calculating. In this case, it's not very
Is
bad for evaluating.
FA E of 2 to the k plus 1 or E of 2k?
E of 2 to what? Fk is
F-
E of 2k plus 1.
Okay.
Okay, so Fk is this, or let's just say A 2k plus 1 is equal to 3 by 4, 9 raised to k, 3 by 4, and A 2k is equal to 3 raised to 2 to the k minus 1, because it's like n minus 1. This is n, and 2 to the k minus 1 is n minus 1, minus A of 2 times 1 plus 1, which is equal to 3 by 4 minus k minus 1. So anyway, like, this will have some similar form, which we don't care particularly about, but you can find it.
A neater form would be for all integers n, it'll be 3 to the n minus of minus 1 to the power of n
minus 1 is to n.
by
What
4.
that is
By 4.
by 4. This is it.
Yeah, that's it.
Amazing. Nice. If you just guess that, you could prove it by induction, but in general, this is like a way to.
I did it with GP. Seems like
Yeah, GP is good. GP is nice. Okay, so let's just summarize the general way to solve a recursion, even if there's a smarter way to do it. So you write it first of all if you have a recursion like this. Okay, I'll just do it in this case. Why not? So you have an is equal to 3 to the n minus 3 to n minus 1 minus an minus 1. So the first thing you'll do is you write it in a way that it's completely linear. There are no constant terms. There's nothing like an square. And so like something like an square is equal to n times an minus 1 is completely unacceptable because you have a square over here. You have an n term. Like all of these things are not enough. It should just be something like c1 times a1 times ak plus c2 times ak plus 1 plus so on till plus c L times AK plus L is equal to 0. So your recurrence should be something of this sort. So like over here, you would just an plus an minus 1 is equal to 3 raised to n minus 1, which is equal to 3 times an minus 1 plus an minus 2. This is the equation which you would get. And then once you get this equation, then you just solve it. So then you try to find all solutions of the form an is identical equal to c to the Jupiter. Okay, so you'll find all solutions of this form, like all constants c for which this thing works. And then you'll try to get, so if your solutions to this are R1, R2, all the way up to Rk, so like ignore the fact that I'm using k many times. Then if you get roots, if you have an equation like this and you try to evaluate it, so you'll get a polynomial and the roots are distinct. Then you have like k roots and k points which are given to you. So you're given the value of a1, a2 up to ak, and you're given this k solutions to it. In that case, you'll just do something like you'll try to find which choice of c1 r1 to the k, like a not k, an equal to c1 r1 raised to n plus c2 r2 raised to n plus so on. We'll try to see which solutions of this. We'll say that these are the general solutions, and then solve the linear equations to find the value of c1, c2, and cn to do it generally. So this is like, but then the point is that here it is good because you have n equations, no, not n, k equations and k variables, right, in this case. So then you're good, mostly. Like you are always good in this case, but that is a little bit of linear algebra. But if you don't get all distinct roots, right? So here you'll get something called the characteristic polynomial, which is like an minus 2 times an minus 1 plus 3 times an minus 2 equal to 0. So this thing, or rather let's say x square minus 2x plus 3 equals 0. Wait, what? Okay, that is weird, but fine. Okay, this thing is called the characteristic polynomial of that recursion. And yeah, so this has distinct roots. You don't have to find the roots. You do if you want to solve it, but you know this has distinct roots, so you're good. But if it doesn't have distinct roots, then that is unfortunate, then you have to do other things, which we will not worry about right now.
That should be CKRK to the power n.
Oh, right. Yes. Thank you. Okay, another. Okay. So yeah, that's you can do to find the general form of an over here. But honestly, it's like so much work. You usually won't do it unless you have to find it for a very, very large value, in which even in that case, powers are very useless. I mean, if you have to find it for, let's say, n equal 2024, even then this recursion will not be of use because then you have to calculate 3 which is not to be done. But sure, this is a good thing to know. But usually you don't have to solve a recursion. Okay, I have a question in chat. How do we guarantee that the roots will be real always? So you don't. That is the answer. Sometimes the roots can be complex, but you don't care about that. You still have a system of k linear equations and k variables, and you can solve it. So in fact, no, okay, I can't think of anything off the top of my head which is meaningful and has complex roots. But complex roots are totally allowed, and you can do the same. Okay. So now let's just do another recursion. So this, I'll just tell you the source of this problem. This was there last year in IQM. Not this. So last year in IQM, there was a question number 8, which had, instead of sufficient, you had only one 2x2 tile. And that was a problem. But when I gave it, I thought it to be sufficient, and I solved it, and because fairly nice, like this, nicer than the intended problem. Okay, so you have a 2x7 rectangle. And now you have to tile it. So you have you tile it on either you have 2x7 like this, or you have a 2x1 domino, or you have, yeah, that is all. So now you have to tile it. How many ways are there? Let you think about this one.
We can't hear your voice clearly, I think.
Can you hear me? Yes.
Your voice is breaking.
Okay, I will try switching to a different net. Okay, is it fine now? Can you hear me?
Yeah, we can't hear you now.
Okay. So, yeah, I hope the problem is clear and let you think about it for some time.
I think I found the recursion.
Okay.
Should I say?
Yeah.
I think it should be like an equals to 2 a in minus 1 plus 2 a in minus 2.
Why is this?
Not only a in minus 1 plus 2a in minus 2. Not 2
Acha,
in
okay.
minus 2.
Right. Okay. Why is this?
Because like if we put the 2 into 2 box in front, it should be a in minus 2 once. If we put the like the 1 into 2 vertically,
Hmm.
then it should be also like the lower gap should be covered. So it should be like a in minus 2. And if we put horizontally, it should be a in minus 1. That's why a n should be.
Yeah. Okay. Makes sense. So yes, what you're saying is key. Just repeat once. I think it's okay. So you look at the last part of it. Look at the last square and just see how you're covering that. So you can cover like let's say this side. So you can either have one big 2 by 2 tile over here like this, or you can, so that if you put a 2 by 2 tile over here, then you just have to tile the remaining n minus 2 along it. So that's like a n minus 2. And otherwise, okay, now leave it. Otherwise, you can put just 1 2 plus 1 in this way, and then you just have to dial the remaining n minus 1 grid. So that's a n minus. And otherwise, like you can also put a 2 cross 1 grid like this, which is annoying. But then this tile in the corner can only be. I am not sure about the answer. I remember the recursion. I don't remember the answer. But like this is the correct recursion. So if you got it, it should be on. So this thing can only be covered with another 2 cross 1 grid. And so that just means ki you still have like an n minus 1 grid to fill. So then that's again another AMH. So that is how you get this recursion. So now you just have to find A7. So of course n is equal to 7. That is what is meant by n. So now you have this recursion, so you can solve it or you can just find out. Okay, so this one I think I'll just do it in the normal way. Just find all the AI till A7 because 7 is small. Anyway, all right. So we have A1 is equal to 2 cross 1 grid. Only one way to dial it. A2 equal to 2 cross 2 grid. 3 ways to dial it. And now we just find everything. So A3 is equal to A2 plus 2 times A1 is equal to 5. And then, yeah, so now I just find everything. I'm not. Okay, anyway, I think this part I'll just leave. You just have to sort of put another values and it will basically work out. You will find some value for it. So Okay, nice. So now let's do some not so recursive problems. I'll give you some Fibonacci. No, sadly, no Fibonacci over here. Okay, so now I think recursion mostly like you've got the general idea. You can practice more. I think I'll find some more problems and send them in for you to practice. This is a good problem. You can try this by induction, but right now, like this is more. Let's do this one. Okay, so you have to show that this thing is always even. Just to be clear, this is floor function. So
This is the IMO-PRQ, I think.
yes, it is an IMO-PRQ. So in case you've seen this before, because it's not a very creative source, you can try this problem. Just take a screenshot. Okay. And you'll try to see how this quantity changes as you vary n. So like as you go from n to n plus 1. So the point is that this floor works very nicely with respect to changing by 1, because the only time an n by k floor is not equal to n plus 1 by k floor if and only if k divides n, which is quite a good case in general. It's nice to have that. So here you just, of course, prove it for n equal 1. You just have n by 1 by 1 floor plus floor plus root of 1. Oh, Athar, yes, go ahead. You don't have to raise
I got
hand.
the main idea. So like,
What?
I think I got the main idea. Can I say it?
Yes, go ahead.
So when you go from n to n plus 1, the increase in the number, the total increase, I think, will be the number of divisors of n and there'll be an additional plus 1 if n is a perfect square minus 1. So like, what will happen is the number of divisors of a non-perfect square is even. So it'll be based on that. And if it's odd, then the square root part will also increase by 1.
Yeah, okay. Good, that works. Nice. Yeah, so since you're inducting, we'll just say f of n plus 1 minus f of n, and that's just summation. Okay, so notice that first of all here, they've only written all the way till n by n ka floor, but you can look at it as also being n by n plus 1 floor and n by n plus 2 floor and all of that. You can look at it as all of those terms being there because they are 0 anyway. Why do you care? So like it's nice to say that you have it's the summation for I greater equal 0 n plus 1 by I the floor minus n by I floor. Plus what? N plus 1. So this thing here to this function, it is equal to, it's mostly equal to 0 if I does not divide n plus 1, but if I divides n plus 1, then it will just be 1. I divides. So then it is 1 only for like the divisors of n plus 1, so that's like d of n plus 1 times it's 1. So this thing is just going to be equal to number of divisors of n plus 1 plus floor root n plus 1 minus root n floor. So the point is that the number of divisors of n plus 1 is usually even. And that's just because of like the bisection key. You have k divides n plus 1, then n plus 1 by k also divides n plus 1. So they come in, the divisors of n come in very natural pairs. And the time when this fails is when k is equal to n plus 1 by k, in which case the same element is counted twice. So that just happens for the root of n plus 1. So if so like here mostly, as long as n plus 1 is not a perfect square, then this and this will be equal and this thing will be even. So we don't care particularly. So this thing will be even if n plus 1 not equal to k square or some k, and this thing will be equal to 0. Right, n plus 1 not equal to k square. But if it is a divisor, then this thing is odd because of the same argument basically. All divisors except the square root come in these natural pairs, and other things are odd. So this thing will end up being odd, and this thing will end up being 1 if n plus 1 is perfect square. So in any case, it changes by an even value, because here it's like an odd number plus 1, here it's just an even number. And since it was even at 1, then it will be even for all natural numbers. So the general vibe is that if you have a problem which has n by k floor, then that's usually nice to think of induction, because it acts with, and how the quantity changes as you move from n to n plus 1, because it will change only when k divides n plus 1. I think it's okay. One last problem for today. Anyone, any ideas? Just I'll give you like 5 minutes to think about it.
The only numbers for which n by, as in n plus 1 by k floored is more than n by k floored will be the factors of n plus 1.
Mhm.
In those
Or-
cases, it will be, so it will be a product over all factors of n plus 1 of LCM of all of 1 up to that factor by LCM of 1 up to that factor minus 1. But from there, I'm not sure how to continue.
Okay. So yes, that is fairly nice. So yeah, if you're again trying to see how it changes, right? So basically what you're saying is that we'll see how it happens when k divides n plus 1, right? When the LCM changes.
Yes.
Okay. So yeah, that is the general idea. VP of both sides? That could work. Does that work? I'm not sure. Maybe. I'm not sure. How would you do VP again?
Like VP n factorial first, like you substitute that other definition, which is n minus SP of n by p minus 1. like the definition for that. And then LCM, like VP of LCM is very clean. You can just define it to be the maximum power. And then it turns out that this expression is always less than the other. Like it's
Interesting. Yeah, I think VP could work actually because
Yeah.
n by k you want to find the maximal power. Yeah, that could work. Yeah, I think probably like a VP argument would also work. I'm not sure if it finishes nicely, but may work out. But also you can just look at how this thing changes if you go from n to n plus 1. And luckily you have a product over here and you have n plus 1 factorial and you have like n factorial. So look at the difference. Just use f of n. Then you look at f of n plus n. Then you can just look at f of n plus 1 minus f divided by f of n. And so, okay, so we want to n. This one is slightly more, it has like slightly more number theory flavor rather than it's more combinatorial. 1, 2, all the way to n by k. And we have to prove that this thing is equal to n plus 1 because like n plus 1 factorial by n factorial. Yeah, so we basically have to see if we call this term as I, if we call n by k floor as I, then when is LCM of 1 to up to I plus 1 different from the LCM of 1 to up to I? Because that's, first of all, we looked at when n plus 1 by k floor changes. Now we're trying to look at when the LCM of those things changes. So clearly you have k will divide n plus 1, but this quantity to not be 1, but more constants.
I think I have a solution now. So if LCM of 1 to I plus 1 is just LCM of 1 to I but I plus 1, so then we can actually just replace this bit, the I plus 1 by the GCD of I plus 1 with the LCM of 1 to I.
I plus 1, yes, fair, okay.
Yes. So there are three cases now for what I plus 1 could be. If it's a prime, then this will just give itself.
Then this will, okay, then this will be I plus 1. Yes.
And if it's 4, then it will give 2. Right? Yes. And if it's 4, it will give 2. And otherwise, it will give 1.
I see. If it is 4, what will it give you?
2.
2. Why? Why will it otherwise give 1? It doesn't otherwise give 1.
I think more general statement would be like if it's prime power k.
Yes. Okay. That is correct.
Yes, it's a LCM, not a product.
Yeah. Yes. I plus 1 is a prime power. That is indeed the case. Because, I mean, if I plus 1 but not be a prime power, which is p times q, p and q are not primes. They're just random co-prime things. Because if it has more than one prime divisor, then you will just have that I plus 1 divides the GCD of these things. 1 to 2. not GCD, LCM of these things, just because P divides the LCM, because like P is actually contained in 1 to I, and Q also divides the LCM. And because P and Q are co-prime, we can get that PQ divides the LCM. But if it's a prime power on the contrary, you have, okay, so the point is that there is no reason for P to the K to divide LCM of 1 to up to I. Because there's nothing in 1 to up to I which has VP of, what do you call it? Whatever it is, A equal to K or greater equal to K. Is never true. Is never true in 1 to I. So this will not divide I. It will only divide, but there is P to the K minus 1 is there over here. So P to the K minus 1 divides the LCM. So what that just means is the LCM of 1 to up to I plus 1 will just be LCM of 1 to up to I times an extra power of P. 1 to I plus 1 by LCM 1 to up to I will be equal to that precise prime P. That is good. So that now that, yeah, you got the main part of the solution. Now we just do some things and it works out. So it's like n plus 1 by k should be equal to a prime times r, and then you will add. So we want all p raised to r, which divide n plus 1, and for all of these values, we'll add an extra power of p. Right? And what can r be? R can be anything from 1 to up to the VP of n plus 1. So what I mean is that when will this is always prime. This thing is always prime. It's always prime, and it is also always a prime p dividing n plus 1. So how many times will a prime, if you take a prime p dividing n plus 1, how many times does it occur over here? It will occur whenever n plus 1 by k is equal to p raised to r. And now this p raised to r takes, basically it has as many values as the highest power of p dividing n plus 1. So you have 1, 2, and so on until whatever p raised to, not k, s. P raised to s is the highest power of p dividing n plus 1. And if p raised to s is the highest power, then you'll multiply by p raised to s, because you're multiplying by once over here and once everywhere. Yes. So that just finishes like this. You're multiplying by p. Is the solution clear? I went over it fairly quickly.
Yeah, it's clear.
Yeah.
Nice. Yeah. That is it. Yes. Now let's just do this one, because we have time for it, and it is quite a nice example of where you would want to interact. The problem is that you have numbers from 1 to n. Like, let's say n equals 5, you will have numbers like 3, 1, 5, 2. Nah, not like this. 3, 5, 2, 1, 4. And at each step, if the number at the start is k, we remove it and place it at the kth position. So like over here, we look at the number which is at the start. It is 3. So what we'll do is we'll do 5, 2, and then at the third place, we just place the 3. And the rest continues, like 1, 3, 4. So now you look at 5 and do the same thing. Take it and you place it at the end, like this. Now again, look at 2 and 3, 2 at the second place, then 1, 4, 5 as usual. And just keep going. So now you have 3, so then 2, 1, 3, 4, 5. And finally, 1, 2, 3, 4, 5. Wow, that arranges nicely. So monovariant, nice. Nice. Yes, there is a monovariant solution. And try to work on that. There is also an induction solution which we are going to do because it's an induction class. But
I think I have a idea with induction.
yes.
Like if we find n somewhere, then the n will go at last and that would never change. So the whole problem becomes on n minus 1 then. And if
Exactly.
we assume on n minus 1, then it would be true for n. But we have to
Yes.
show that the n always have a chance to go at last.
Nice idea. But hello. Well, first of all, if n was already at the end, then it's never going to come back. But also, if you have n equals 6 and you have this combination, then these 5 and 6 are kind of fixed over there. There's nothing that's going to change them. So I don't think n, it's not true that n always comes to the start. But if it does, then we are done. But yeah, nice. Good work. Quite useful. So like this 6, 5 will basically just stay there and not do anything. The 4, 1, 2, 3 will keep shuffling. 2, 1, 3, 4, 6, 5. 1, 2, 3, 4, 6, 5. So even though n was not at the start and did not ever go to the end, we still like that's possible. Okay. Okay, so yeah, if n ever comes to the start, we're done, and not just to the start. Like if n ever is at the end, let's just say that. And that's
We can think of like dividing 1 to n into two subsets, like 1 to k and k plus 1 to n. And if like from k plus 1th position to nth position, the k plus 1 number to n numbers are like permutated in any order. So like
yes.
this problem generally becomes to 1 to k.
Yes. Nice.
Uh,
Yeah, that works. I see you got it. I can see that. Okay, so what you're saying is that over here you have like 6 and 5, which are the last two numbers, and they are the last two positions. So they just don't talk to the rest of the diagram. It just remains that way. So like we basically don't care about the 6 and 5. We can then just look at the permutation, that is 2, 4, 1, 3, and use induction to finish, because you've got the smaller keys by getting rid of those last few terms. So the real problem is you have n stuck over here, and then you have k stuck. And it's at the kth position, and then you have a case on it. It's just not disturb the n. So like what I mean is that the n will after a point get very close to the first position. So if it reaches the first position, then we are done. But otherwise, it will just reach here and then get stuck. Like these other numbers will keep permuting among themselves, and the n will get stuck over here, like forever. So the case which we have to worry about is that, so we have to, if we show that n is at the kth position, if we show that these are 1 to up to k minus 1, then we would be done because induction, because these things are just moving around among themselves. So you can just not worry about this part of the sequence, because that never really changes. But if that's not true, then we have to think of something. Because like if this never moves, that just means key. Okay, first of all, this thing is not one. Don't think of it as something random. So the point is that whenever something comes to the start, if some s comes to the start, then if the s were to be greater than k, or let's just say greater equal to, then it would end up displacing the n, right? Because if you have like k equals 3, let's say, then you have 3, 4, 5, 1, 2. Here, like n equals 5, k equals 2. Then this 3 will go and displace the 5. It will go and sit over here and displace the 5, so it gets closer to the start. But that just means that everything which comes to the start, everything which reaches the start is less than k. Okay, so what we'll do over here is instead of worrying about only this n, right, we have the n never reaches the start. Okay, not just that, we have that n is stuck. By stuck, I mean it will never get closer to the start than this. This thing number will just keep shuffling up. But so like here we'll just try to look at which numbers will eventually get stuck. Right? Because if okay, let's just see. You look at which numbers get stuck. Because once all of the numbers which have to get stuck have got stuck, right? Because that will happen after a finite number amount of time. So after that, you will have something like, okay, you'll have a random sequence a1, a2, an. But the point is that everything which reaches the start is less than like the number, everything which reaches the start. So let S be the set of numbers which get stuck eventually. Set which gets stuck. Okay, so everything else will eventually reach the start. And it will keep reaching the start infinitely many times. Because it doesn't get stuck. Just start infinitely. So like let be T. And the point is that every element in T, some small t belonging to T and some S. S is the set of okay, so S is belonging to S. So that all of these values, which are like the T values, which are in the beginning, because the thing is that so what I'm saying is that S will be some block like this. It's not going to be a random set like one element from here, one element from here, etc. Sorry, very sorry. Okay, moving on. S is some set like this, because the point is that if you want to displace some element in T, right, let's say that you have an element of T over here, and before that you have an element of S. Then what will happen is that this T will move closer, and sorry, T is the element over here, this thing is T, and this is an S. Then if you want to move the T closer, then the S closer to the start, and S will also move closer to the start. But that's like not allowed because S is a set of elements which get stuck. Right? And we also have S non-empty because we have N eventually gets stuck. So S is not equal to the empty set. Right? So now, yes. So like S, S is some set like this, and everything before it reaches the start infinitely many times. But look at the argument over here. Everything which reaches the start is less than equal to k minus 1. So if S is equal to positions like a k plus 1 all the way till a n, right? So like this first element is a k plus 1. Then what that is saying is each of the other a k, which is in T, right? So each of those I one is equal to I is equal to k. Then each of these ai is less than or equal to k, right? Because if it was at least k plus 1, that would go and displace the elements in S. So yes, this just means key. So you have a1, a2 up to ak with all of the ai less belonging to 1, 2 up to n up to k. Sorry, what does this give me? Come on, please.
Then this would have to be the remaining elements which are greater than k then?
Which one? S, right? Yes.
Yes.
But the point is, what is T? T is just a permutation of 1, 2. So like we cannot worry about S, and we only have to worry about T. Right? Okay. This argument is a little bit scuffed. It's not the same. So like I'll just quickly go over what I was trying to do. So we have N, which eventually gets stuck, right? Unless it reaches the start, in which case we'll go to the end. So the point is that all the number, there's some set S of numbers which eventually get stuck. So the first thing which you will do is you'll say, let the algorithm go over as many times as it has to, so that every element in S is like finally stuck. It's not going to move after that finite amount of time. Right? So this A1 up to AN, which we have over here, it is not the original sequence which we had. It is a slightly modified version where you have all of the like you have the original sequence S1, S2 up to Sn, terrible notation. And then you will run over the algorithm, and eventually you'll get to A1, A2 up to AN. And like this is the point at which everything has got stuck. Like all the elements which had to get stuck have got stuck. So the key part is that all the elements which do get stuck, they will end up at the end. Because if you have an element of S over here and an element of T over here, then no, not like this. Sorry. If you have an element of S over here and an element of T over here, and you want to move the element of T because that does not get stuck, then you would also have to move the element of S. Right? And you will not do that because like S has got stuck. And then to finish, you just say that everything else reaches the start infinitely many times, because otherwise, if it doesn't reach, then it would have gotten stuck somewhere. And then you'll just do this. All the other AI for one less as k are at most k. So then it has to be a permutation. And then you end up. Okay. Does this sound alright? Or also like you can ask about motivation. It wasn't clear. I will take that as a yes. So yeah, this is I'll just, for the sake of completeness, tell you the slightly shorter solution of this. That is easy. So the point is that if n never reaches the start, and if n is at the kth position, and n is at the kth position, never reaches starting, never reaches end, and n is at the kth position. Kth position, then you'll just have that not even like k also never reaches the start, because if k were to reach the start, then it would go and displace the n, and then it would keep them. So then the point is k never reaches the start, n also never reaches the start. So they are not doing anything. It's just like a placeholder. The n and the k, both of them. So they're just like placeholders. They're not actually doing anything because they never reach the start. So now the magical part is, does it matter if you swap the k and the n? Because they're not doing anything anyway. And of course, it doesn't. Because like, what are they doing? They're just placeholders after all. So you can assume that your k, that your n is at the end, and then just induct.
That's more like cheating, not magic.
Yes. Okay. But this is I like this solution more. I don't know why. Mostly because it's my solution. But okay. Um so like is this one clear, and the motivation, all of them? Any questions
Yeah.
about?
Yeah.
Okay, great. I guess I'll stop recording. We are already late. So I'll stop recording.